Everyone. So today we're going to cover chapter 9.1 of the Griffiths. So this whole chapter is on quantum chromodynamics, and chromodynamics is the description of the strong force. Well, we can talk about that in a second, but the important thing is that all of the stuff we learned from on quantum electrodynamic QED, right? Then we started that with the Dirac equation in chapter 4, and then we went through the spinor in chapter 5, and then we did a couple of examples of annihilation process and scattering process with electrons. All of that is still going to come in play because quantum chromodynamics is based on QED, but now with this additional charge called a color that we are going to have to quantify in order for us to figure out, which processes more likely, which processes less likely. However, you can actually not compute cross sections by hand, or even with, a computer to in an analytical fashion, because the strong force is actually non-perturbative. That means every time you calculate a Feynman diagram, there's always going to be another Feynman diagram that's a higher order that's just as important as the previous one. So you can never actually get to the full answer. Okay. So let's review quantum electrodynamics real quick, right? So we found that in chapter 4, right, the solutions to the Dirac equation are these spinors, right? These little U's and V's, right, where it's a 4-component spinor. And, these 4-component describes, whether something is a particle versus an antiparticle, and also whether it has the right or left-handed helicity, okay? And then the rest of the solution is just, plane wave, right? And then the idea is that if you can find these, the answer to all these plane waves, as long as you can add up all these combination of plane waves, you actually have the complete solution. Okay, and these 4-component spinors are described with these equations down here, right? Where you have the particle that has a right-handed helicity, and then a particle that has the left-handed helicity, and then the antiparticle with the left-handed helicity, right-handed helicity, and the antiparticle with the left-handed helicity. Okay, so in quantum chromodynamic, what we're going to do, unlike QED, where there's only one charge, okay, there's, even though it's a positive or negative charge, right, you would think there's 2 charges. There's really only one type of charge, the electric charge, right? You either have positive electric charge, negative electric charge, or 0 electric charge. So this is a one-directional thing. In quantum chromodynamics, okay, there are actually 3 different charges, okay, and these are called red, blue, and green charges. Okay, so each of these colors are a different type of charge. Okay, so of course the quarks are not actually color in the physical sense. You don't see a red one, blue one, and a green one in there. It's just a metaphor that this 3 strong charge aspect of QED just emulates our actually visual senses, where our eyes are actually have the ability to see 3 different colors also. Okay. All right. So this adds a new degree of freedom to the possible solutions to the eigenstates for quarks. So this gives us a set of column vector called C's. Okay. So there's going to be for red quarks, it'll have a C of 1, 0, 0. For a blue quark, right, it'll have a C of 0, 1, 0. For a green quark, right, it'll be 0, 0, 1. Okay, so the first component is the indicator whether it's red, the middle one is blue, the last one is green. So if you have a C equals to, let's say, -1, 0, 0, okay, that means that's actually have a color, it's an anti-quark of red, okay? But usually they keep track of the particleness versus the anti-particle with the U's and the V's instead, okay? All right, so this little color vector, right, is just going to be called CI, where I runs from 1 through 3, right, 1, 2, 3 components, okay? And each quark carries a single color, right? So an up quark, right, could be, would have a C equals to, let's say, 1, 0, 0, right? Another way to write that is that C, right, is going to be C1 equals to 1, right? Where other, right, is equal to 0. Okay, we're going to write this in a little bit different terminology in a second, but we need to put in the gauge boson also, okay? The thing that is being exchanged between the quarks are not photons. Well, they could exchange photons, but also they can, since we're talking about the strong force, they are going to be exchanging gluons for the strong force. This is different from the QED because the gluon actually carries charge also. In fact, it carries two different colors charge, okay? Right, this is very different from quantum electrodynamic where the photon was neutral. Just remember when there was like a photon coming in, right? This photon cannot connect to other photons, right? You can't draw something like this. This is not allowed, right? Because, right, since the photon has no charge, it does not itself couple to other photons because you need some charge in order for you to make a vertex. Gluon itself has a charge. Right now, we're allowed to connect gluons together. Okay, so for example, in this case, maybe this is a red-blue bar photon, and maybe that the one down here is a blue red bar photon. So when these comes out, combined together, right, it actually is a red-blue bar plus a blue-red bar. Okay. And for normalization purpose that we'll see is that we're just going to have to divide by 1 over square root of 2. Right? It doesn't end here. Right? You can also have something like this, where you have our good red-blue bar gluon coming in, the blue-red bar gluon coming in. Instead of combining into single gluon, you can have two gluons coming back out, and maybe the blue-red comes out this way, the red-blue comes out this way, right? So and so on. You can have like 5 gluons connecting to the vertex, step 6, 7, infinite. Now, hopefully, you can see why this chromodynamics is actually not calculable by analytical method, where you just take this diagram, calculate the Feynman diagram, calculate the follow the Feynman rules, and then have a matrix element, and then square it, and then add that to your cross section, right? You would have to do infinite number of diagrams in order to do this. The interaction between gluons and quarks also changes the color. The reason you can't do this is that, let's say you have a red quark coming in, and then a antiparticle blue quark, right? So this actually brings in, right, the direction. So this is bringing in a red colorness to it, and this is actually bringing in an anti-blue colorness to it. Okay, this combines together to give you a gluon that is red and anti-blue. So that's why there's always, these gluons are always going to have a little bit of the particle colorness and a little bit of the anti-colorness part of it. Since there are 3 different colors, there's actually 9 possible combinations of gluons. Okay, and these combinations can be anything, right? But so far in our universe, right, we found that the gluons always exist in these what's known as the color octets, which means 8, right? And then we have a singlet, which means 1. Um, and these are actually the states that we found gluons in our particular universe, where one of the possible state is actually this R blue bar, and then blue R bar. So it's a little bit of it's red and then anti-red in it, and then also blue, anti-blue, and blueness in it. Okay, and due to the fact that all these states has to square to 1, when you have this, then you have this square root of 2 underneath in order to keep the normalization. So that is the normalization is to 1. Okay, and then you also have this version of it where it's kind of like the complex version of it in the complex plane with a negative I in front. You can also have R bar minus BB bar. Okay, so this is also a gluon state that we find. There's also like these 3-state version, 3 different color version, was RR bar, BB bar, and then it adds a factor 2 with the green color in it. And because you have to normalize this to 1 also, you're going to see that it has to be a square root of 6 in order to do that. Okay. In addition to this, there's also the singlet. Okay. And the singlet means is that it's a combination of all 3 color with this anti-color combined together. Okay. And the normalization for that is, of course, going to be square root of 3. Okay. This is possible. Okay. However, it has never been observed yet. Okay. So in our universe, we only see these 8 different types of gluons that's found in equation 9.4. Okay. So in order to quantify this, as opposed to keeping track of all these R's and B's and stuff like that, the gluon is kept track of with a yet another column vector, right? Just like what we did with the quark, where we define this to be some C, right? With some component up here with these 3 components. Okay, you do the same thing with the gluons, but instead of having 3 components, now we're going to have 8 components. Okay, these are going to be these A column vectors, and for whatever reason, even though we're counting from 1 to 8, which you would think would use a Roman letter, Griffiths decided to use alpha, and that's so it's a Greek letter. You would think you should start counting from 0 with that, but he decided to use alpha instead. Okay, so this also still start counting from 1. Okay, where this A column vector, right? If it's the 1 at the first component, it represents the first octet, right? This one, right? If it's 1 at the 7th component, right? It represents the 7th octet, which is this minus I blue green bar, and then minus green blue bar with a square root 2 for normalization. All right. So the thing that the gluon do have a commonality with photon is that the gluons are also massless and has a spin of 1. So we represent their polarization and momentum in a similar way as what we did with the photon, where it's always these epsilon and epsilon star, right? That's what represents photons in QED. You do the same thing with gluons. Okay. So we're going to introduce a version of Pauli matrices, but since QCD is more complicated, right, we're going to have a different version of it. These are called the Gell-Mann lambda matrices. Okay, and these matrices are 3 by 3 for 3 colors. Okay, and these lambda matrices are defined as these. Okay, and this is done after years and years of work that makes these matrices. They're orthogonal to each other, and they also have the same commutation relation as the Pauli matrices. Okay, that's why these matrices were chosen like this. Okay, so these Gell-Mann matrices follow the commutation relation, and this is kind of a little bit more complicated than the Pauli matrices, where if you have, let's just do an example here. Okay, let's do lambda 1, lambda 2. Okay, what this tells you is that the commutation relations between them, okay, is going to be F. Okay, so this letter is the alpha, this letter is the beta. Okay, so this is 1, this is 2, right? And then this is some third index gamma, where this will be equal to lambda gamma. Okay, so gamma can go from 1, 2, 3, all the way up to 8, right? Okay, so these Gell-Mann matrices, they commute with each other, but then their commutation is a little bit more complicated because they are larger matrices. Okay, and these factor F, right, that tells you whether or not something commutes or not. Okay, right, are defined as below. There's actually many more of this, but the rest are 0. That's why it's not written. So F123 is actually 1. Okay, it's the only one that's 1. Okay, but there are other combinations of, what you put in. So if you want to do 147, right, you're commuting 1, 4, right, and then equals to 2 times I, and then F147 is 1/2, and then you have lambda, the last one is 7, right? That's the commutation relations between them, okay? So therefore, when you have lambda 1, lambda 4, minus lambda 4, lambda 1, right? That's what the commutation relation is telling you. That's going to be I times lambda 7. And we'll have you guys check this in the homework, okay? Okay, so the ones that are not here, right? F not here, right? Right, are all 0, okay? Okay. There is some interesting pattern to this. Notice that each of the letter has to be the same, right? Has to be different, right? Because hopefully that makes sense. Because lambda 1 commuted with lambda 1, of course that's going to be 0, right? So it wouldn't make sense for the same 2 letters to exist. Sorry, same 2 numbers to exist. Griffiths also used what's known as the slash notation. It's just a way to shorthand a couple of things that we did in Thompson. So remember, a lot of times that you have, let's say like Q gamma mu, right? Where is some 4 vector times these gamma matrices, right? The way that Griffiths deal with this, instead of writing that, what they do is they just do a little thing called a slash notation. That's exactly the same thing, okay? Or if you have P slash, that's equal to basically P gamma mu, okay? It's just a way to shorthand that. I think people stopped using that because that's also confusing, because the slash also means you're canceling out stuff. So I think people just stopped using that. But however, at the time that Griffiths wrote this book, it was still used. Okay, so let's go over the Feynman rules for quantum chromodynamics. Okay, and I'll highlight the difference from the electrodynamics that you guys are used to. Okay, so if you have, let me just draw a simple Feynman diagram here. Right, let's say you have a quark scattering off each other, exchanging a photon. Okay, so this will have some momentum P1, this will have some momentum P2. Ooh, one more thing to note. Well, let's deal with this next section. P3, P4. Okay, this is the Q that's being exchanged between them. Right, it's going to be, of course, P1 minus P3, or the same thing as P2 minus P4, right? Actually, opposite of that. Okay, so if you have an incoming quark, let's say this one is a quark, right? What you do is you write that it's a U spinner, okay? In this parentheses, S is to help you indicate that, okay? Whether it's the helicity up or the helicity down, so that's what this S stands for in Griffiths. Okay, you have to write down the momentum. That's a function of the momentum. And the difference here is that now we have this additional factor, which is this 3-component color vector, right? That tells you what color the quark happens to be. Okay, so if this was a quark that is spin up with a color of red, then this C column will be 1, 0, 0, right? Okay, and you will use the U spin up, right, as a function of P1, right, for that. Okay, all right. For outgoing particles, which is the stuff on the right hand side, right? Since this is going to conserve, let's say this conserve the spin and the color of this. I don't think actually it could. All right, let's make this the B bar, right? The outgoing B, sorry, with the blue color, right? And the way you write this is that this will be U up still, P3, right? And the color vector here, right, will be equal to 0, 1, 0, right? Okay. You have the anti-quark version. Of course, you're going to use the anti-particle spinners. Okay. Okay. Oh, sorry. And this also have the dagger version of it, meaning it's the complex conjugate, but then you change the row vector into the your column vector into a row vector. It's the transpose also. All right. So for the antiparticle, you do the same thing where SQED, where you have the antiparticle spinners, right? This can be up and down, okay? And then, right, the same thing as the previous, where the incoming, right, has the C dagger, and the outgoing is the one that has the non-dagger version of it, okay? Okay. In case there are diagrams that, you have gluons like this, let's say, changing into a quark, and then, right, then you have another gluon here, right, where the solid lines are the quark line, the circle lines are the gluon lines, right? You can have incoming and outgoing gluons. Let's draw one that has an outgoing gluon also, like this. Okay. So similar to photons, right? They are represented by these polarization vectors. Okay. Okay. But in addition, right, since the gluon has color to it, has 8 different possible colors combinations to it in the octet, right? We have to add this additional factor of A alpha, right? And then for the outgoing gluon, this one, right? This is for the incoming. This one's for the outgoing, right? You have this 8 element column vector A alpha, but then you take the complex conjugate of it, of course. Okay. Whew. All right. Next, we have the propagator, right? The propagator can either be the quark, or the gluon, right? So that's the stuff that's being exchanged, right? Highlighted there. Okay. So if it's either quark or anti-quark, right? Since quark have mass, the propagator factor is I times Q slash, right? Remember this Q slash actually just means Q gamma mu, okay? Plus MC, just like you did with the fermion, and then it's Q squared minus M squared C, well, C squared. In Thomson, you wouldn't have to deal with the C's, but in Griffiths, he didn't use natural units, so we've got to just make all the C's equal to 1, okay? For gluon being exchanged, right, that's very similar as a photon. Instead of in place of I g mu nu, it's going to be Q squared. And on top of this, there's this little delta alpha beta, where this delta alpha beta just shows that the is indicating which color gluon is being exchanged between the two. Okay. Right, and we're going to see this explicitly when we get to actually trying to write down the matrix elements for these Feynman rules. Okay, the vertex factors very similar also, but okay, this is where these Gell-Mann matrices comes in. Okay, it's the same thing if you have a quark gluon vertex, right? It's the I as opposed to just the electron charge. This is going to be the strong force coupling constant. Typically, that's going to be about 1. Okay, and you have a factor of 1/2 there. But these lambda alpha are the particular Gell-Mann matrices that you're going to have to multiply by in order for you to create a 3-component thing times this 4-component gamma matrix in order for it to multiply properly. So what's actually happening is that you're going to sandwich this. So let's do minus RGS 2 lambda. So that's just a number. I'm going to put this in front, right? And then you have gamma mu back here. So these are 4x4 matrices, right? These are 3x3 matrices. Okay, so what you do is you actually have a 3-component, right, row vector here on this side multiplying this, and then you have a 4-component spinners here, right, being multiplied by these gamma matrices. So you just have to multiply the right thing to the right stuff. Okay, so the color stuff, they multiply into each other, and then the spinner stuff, they multiply into each other. Okay, and you can see how this turns into a big mess very quickly, right? So I mentioned before, right, gluon has colors, so therefore they actually self-couple. So you can have these gluon combined together, and then it makes a new gluon. The vertex factor here are these complicated so basically the g mu nu, which is this simple tensor, okay, but multiplied by different Griffiths doesn't just use P all the time. They use K as the momentum. So these K's are the momentum vectors. Okay. Vectors. Okay. So these are K1, K2, K3 here. Okay. And you have to get to calculate all combinations of them in order to get the vertex for these 3 gluon vertex. Okay. It is possible to have 4 gluon vertex. Okay. And we're gonna just look at this. Okay. And this just turns into bigger and bigger mess as you write more and more gluon vertex together. Okay, and there's a 5th one. You have 1 to 5, 6, 7, 8, 9, 10, and on to infinite. Okay, so all these gluon self-coupling is going to create a big mess in the calculations. Okay, all right, so that's the Feynman rules for the quantum chromodynamics. Hopefully the slight change in notation between the two books is not going to bother people too much. If there's a question about that, just literally just ping me on Slack. There's this Q/ thing, and Griffiths also uses. So if you have, let's go back up to this diagram. Let's just use the. He used P up there also. Interesting. But sometimes he used K. I guess he used K's for the gluon lines. So in this case, right, up here, right, he's using K as the momentum. These are just the momentum vector using K instead of P. Okay, so don't get confused by that. What's the other thing that's different? You got that. Oh, and yeah, he doesn't set C and H bars to 1. Therefore, whenever you see that, just make it equal to 1. All right, so that's it, and I will work on the next lecture.